Alright, here in section 2.1, we're going to do a quick preview of calculus. And in this section we'll understand what calculus is and how it compares to pre-calc, understand the tangent line problem and how it's basic to calculus, and the area problem, which is also basic to calculus. So what is calculus? Calc is the mathematics of change. For instance, calculus is the mathematics of velocities, accelerations, tangent lines, slopes, areas, volumes, arc lengths, centroids, curvatures, and a variety of other concepts that have enabled scientists, engineers, and economists to model real-life situations. You know, that's a big part of mathematics, is using mathematics to describe the world around us and maybe make predictions about how things will behave in the future. Although pre-calculus mathematics also deals with velocities, accelerations, tangent line slopes, and so on, there is a fundamental difference between pre-calc and calculus. Pre-calculus mathematics is more static, whereas calculus is more dynamic. And here's a few examples. An object traveling at a constant velocity can be analyzed with pre-calc. To analyze the velocity of an accelerating object, you got to use calculus. The slope of a line can be analyzed with pre-calc math, and that was a line. To analyze the slope of a curve, you got to have calculus. The curvature of a circle is constant and can be analyzed with pre-calc mathematics. To analyze the variable curvature of a general curve, you got to have calculus. The area of a rectangle can be analyzed with pre-calculus. To analyze the area under some odd curve, you're going to have to use calculus. Each of these situations involves the same general strategy: the reformulation of pre-calculus mathematics through the use of the limit process. So, one way to answer the question, what is calculus? It's to say that calculus is a limit machine that involves three stages. The first stage is pre-calc mathematics, such as the slope of a line or the area of a rectangle. The second stage is this limit process. And the third stage is our new calculus formulation, such as a derivative or an integral. We'll be learning about those all year long. So we take our pre-calculus mathematics, we apply this idea of a limit, and we come up with calculus. Some students try to learn calculus as if it were simply a collection of new formulas to be memorized, and this is unfortunate. If you reduce calculus to the memorization of differentiation and integration formulas, you'll miss a great deal of understanding, self-confidence, and satisfaction. So the notion of a limit is fundamental to our study of calculus. The following brief description of two classic problems in calculus. We have the tangent line problem and the area problem. And this should give you some idea of the way limits are used in calculus. In the tangent line problem, you're given a function f and a point P on the graph and asked to find an equation of the tangent line to the graph at that point. So here the darker black line is our curve, f of x. We have this point P on the curve, and we're trying to find the equation of this tangent line that hits our curve at that specific point. Let me see, and I'll bring up this here. So we have this point B, and we want to find the slope at that point B of the tangent line. Well, to come up with the equation of a tangent line, we got to have 2 points. So anywhere else on the graph, on the blue parabolic curve I have here, I have this other point A. And if I have point A way up here, I can connect those two points with a secant line, and I have the slope of that tangent line. Well, it's not a tangent line yet because it does cut through the curve. That's why it's a secant line. But the slope of that red line, AB, is 3.64. And you know, that's a decent estimate, but we get a better estimate if I slide point A down the curve closer to point B. And now we can see our slope here is down to 3. But we're still, you know, pretty far away from point B, so I can grab point A and keep moving it down, and watch what happens to the slope. The slope is getting smaller and smaller, 2.8, 2.7, 2.6. The closer I get to B, the more this red line becomes a tangent line, and the more we can figure out the slope of that tangent line where we hit the graph at point B. And the closer and closer I get, the better and better estimate I get. And at some point, I'm going to get right on top of point B. And look at that. It looks like if I go a little bit past point B, now we're under 2. On the other side of B, we're above 2. So, you know, it's probably going to be that the slope at point B is 2. And then, here's the picture from the book that just did, or is trying to show you what I did dynamically. We have our 2 points. We're sliding that point down the curve, getting closer and closer to this point of interest. And our secant line moves down, 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 and eventually it's going to become a tangent line. So what is the slope of that secant line? The m of the secant line, the slope of the secant line, remember it's just delta y over delta x, the change in the y coordinate over the change in the x coordinate. And we can look at it this way. Our numerator is our change in y, or f of c plus delta x minus f of c, divided by our change in x values, c plus delta x, and then minus the original point c. Those c's are going to cancel, so what we have here is our numerator is still that change in y, f of that c plus delta x minus f of c, and it's divided by delta x, how far we've moved on the x-axis. The smaller we make delta x, the better and better our slope estimate becomes. On the other hand, we have the area problem. Again, calculus comes from 2 major questions. What is the slope of a curve at a given point, and the area under an odd-shaped curve? Here we have a weird-looking curve. We want to find the area under it from point A to another point B. In the tangent line problem, you saw how the limit process can be applied to the slope of a line to find the slope of a general curve. A second classic problem in calculus is finding the area of a plane region bounded by the graphs of a function or functions. This problem can also be solved with our limit process. In this case, the limit process is applied to the area of a rectangle to find the area of a general region. So if we want to find the area under this curve, or at least a good estimate of it, we can break that area under the curve up into some rectangles. The rectangles, we know how to find the area of them, and we can do that with just basic math. So if we use 4 rectangles, and here we're going to keep our rectangles under the curve. As I plug in, whatever this x value is at point A, I'm going to go up, hit the curve. That's the height of my first rectangle. At my next x value, I'm going to go up, hit the curve, and go over to my next x value, and that's the height of that rectangle. And we continue doing that, finding areas of rectangles, and most of these are lying somewhat under the curve. So if we use 4 rectangles, here, let me erase this. Here we have some area that's under the curve that's not in the rectangle, so this area went uncounted. Here we have a little bit of a rectangle that's above the curve, so that is sort of an overestimate of the area under the curve, and we got this little corner here too. But again, we're just trying to find an estimate. If we use 4 rectangles, that's probably going to get us pretty close. But what would be better than 4 rectangles? How about 8? Chop it up into more. And now, before where we had this big gap was uncounted area under the curve. When we increase our number of rectangles, now we have a little bit less that is area under the curve that's not counted in our rectangles. And the same thing here. Here's some area that's not counted in our estimate. And we still have these little chunks that are overcountings of our estimate. So, 8 rectangles is going to be even better. In the most astounding events ever to occur in math, it was discovered that this tangent line problem and the area problem are extremely closely related. This discovery led to the birth of calculus, and you'll learn more about the relationship between this area problem and the tangent line problem when we get to the fundamental theorem of calculus. So if we use 8 rectangles, we're better. What if we used 16 rectangles? Cut each of these in half again. We'd have an even better estimate of the area under that curve. And if 16 is good, then cut all those in half and we'd have 32. The idea here is the more rectangles, the better the estimate. Eventually we'll get to the point where we can use this limit process to say I'm going to chop the area under this curve into infinitely many rectangles of infinitely thin width. And that will give us not just a good estimate, but the exact area under that curve. So the assignment for tonight, page 67, 13579. To help with a couple of these problems, I think it's especially 7 and 9, I'll make a second video where we do some explorations that are very similar to those type of homework problems. Might clear up any confusion you have on them. So give those homework problems a shot and look for the second video for section 2.1.